Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 122, Digital 2. Today we're going to have a discussion about cascaded counters. So our objective today is basically use cascaded counters to count higher than the single modulus. An example is a single counter, a decade counter. You can only count from 0 to 9, i.e. 10 positions. We want to go beyond that using a cascaded configuration. The second thing we're going to be able to do today is we're going to use them to count in any number we want to, and additionally use some special frequency division techniques. So basically we've seen that we can make counters using a number of JK flip-flops equal to the number of bits we want. So in theory, if we wanted to make a 1000-bit counter, we could just take 1000 JK flip-flops and just string them together. And for obvious reasons, this isn't practical. So chances are, if you grab a TTL counter off the shelf, it's going to be either a decade counter or a 4-bit counter, like a modulus 16 counter, like a 74190. That's a decade counter. 74163. That's a 4-bit modulus 16 counter. And by themselves, you can only count to up to 10 positions or up to 16 positions respectively. But by arranging a couple of these things in a cascaded manner and making use of their special terminal count and count enable pins, you can count to higher than 10 or 16 places. Okay, so let's just take this right here is the low order, and this is the high order in our counter configuration here. And when a counter is enabled, it's allowed to count. And that's what the count enable does. The terminal count, also called TC, terminal count, also called ripple count out, and in some cases max/min in the case of an up-down counter. So it's the same thing. Just I'm going to refer to it as TC for everything. This guy, when does that guy go high? Well, it goes high only when it's achieved its maximum in a up counter configuration or its minimum in a down counter configuration. So let's go ahead and do an example here. This particular low order portion starts out at quadruple 0, and it's going to progress to 1, 2, so on and so forth, up to 9, and then it's going to recycle. The terminal count for the low order, it's always going to be 0 until it reaches the maximum count of 9. It recycles back to 0, and your terminal count goes back to 0. Okay? So what happens when you do with a cascaded counter configuration, what you're going to do is take the terminal count from the low order and feed it to the count enable of the high order. Okay? So now both these guys are getting the same clock. Right there. And let's again, this is still a modulus 10 right there. And by the way, the first stage is always enabled. Okay, so now our high order, given that terminal count for all these guys was 0, the high, regardless of what's going on in the low order, it's always a 0. But when it's reached 9 at this position right here, TC is 1, and since it's being fed to the count enable of the high, the next clock pulse comes along. What happens here? It goes to, it counts as it recycles. So in effect, what you're getting here is the high order bit for here is reading 0, low order 0. So 0, 0. 0, 1. 0, 2. Now you've gotten to 0, 9. What's the next step? 1, 0. And so on and so forth. 1, 1, 1, 2, up to 1, 9. Terminal count has reached its maximum. The next clock pulse comes along, allows this guy to count 2, 0, 2, whoops, 0. We're counting higher than 10. On and on and on and on till 9, 9, and everybody recycles back to 0, 0. We've just created a 0 to 99 counter. Basically, it's a mod 100. Excuse me, modulus 100 counter using 2 cascaded counters, 2 cascaded power of 10 counters. So overall modulus of cascaded counters is a product of their separate stages. In this particular case, we've got a 10 and a 10, so 10 times 10, we can count to 100. If we put another one, a third stage on here, 10 times 10 times 10, we could count up to 1,000 or 0 to 999. Another 10, 10,000. You know, here's a modulus 16 counter. It's going into 10. What is our ultimate modulus for these configurations? Well, it's 16 times 10, 160. So another neat thing that we can do with these cascaded counters is do some frequency division. Given that the terminal count for this particular counter, because it's a mod 10, it goes high only every 10 clock pulses. So what's the frequency of terminal count given this frequency coming in here? Well, it should be every 10 of that, 1/10 of it. So F divided by 10. Okay, so given this time of diagram here, this is the clock. Let's go ahead and do an analysis of Q0, Q1, Q2, and Q3. And for our purposes here, we really want to check out is TC right there. Just confirm that every 10 pulses, we're getting a output on TC. So clock, and this is let's do a synchronous up counter in this particular case. So Q0 is going to look like this, and that's Q0. And notice that the frequency of Q0 is half that of the clock. So let's pretend each one of these divisions, 0, 1, 2, 3, 4, those are milliseconds. So what's the period of the clock pulse? 2 milliseconds. What's the frequency? 500 hertz. So how long does it take for Q0 to repeat itself? 4 milliseconds. Our frequency, 250 hertz. We've done a frequency division, basically making it half. That shouldn't come as a surprise to you. You've already seen this in some of the other applications. So what does Q1 look like now? Well, it's going to be half the frequency of Q0 ordinarily, but remember, we are doing a decade counter, so things may change with Q1, Q2, and Q3. So I'm just going to go ahead and fill out what Q1, Q2, and Q3 look like, given that it's a decade counter. Remember, decade counter, it's going to recycle at 1001, not at quadruple 1, like a 4-bit 16 modulus. So I'm going to fill out these Q1, Q2, Q3, and I'll be right back. And here's what Q1, Q2, and Q3 look like for a decade counter. Yes, and if it was a modulus 16, it would look slightly different. What's happening here is, let's give our states right here. Currently, in this position, we've got 0, 0, 0, 0. Actually, let's read it MSB to LSB. So it's 0, 0, 0, 0, 0, 0, 0, 1. We've counted up to 1. 0, 0, 0, whoops, 1, 0, count it up to 2, 3, 4, 5, 6, 7, now we're at 8, and all this whole time, TC has been staying low. Now all of a sudden it hits 9. 1, 0, 0, 1. TC, since it's reached the maximum of its upcounting sequence, goes high. Boom, everything recycles. Back to 0. And we can start all over again at 0, 0, 0, 0. So what signal is being fed to the second stage? It's this guy right there. Next clock pulse on that one here, what's going to happen here, basically it's a repeat of the low order stage, but the only thing is, the only one that's going to change, that guy right there. Q0 will change in this stage. So we're talking about frequency division. Okay, what's happening here is Q0, we already discussed, it's half the frequency of the clock. What's the period of Q1? Well, it's half the frequency because it takes twice as long of Q0, so 125 hertz. And now what's the frequency of Q2? Well, it takes twice as long, so 62.5 hertz. But now Q3, what is Q3's frequency? Well, Q3, yeah, normally if it was a 16 modulus counter, it'd be half of that, 31.25, but we're not. It's a decade counter, so what is this period right there? Well, if you do the math, it should be, I think it's like 20 milliseconds right there. So you're getting 20 milliseconds. In effect, what you're doing is f divided by 10, as we previously discussed up here, you're getting 50 hertz. Okay, so now what's the frequency of TC? As we just said, repeats itself every 20 milliseconds, so we're getting a 50 hertz signal right there. So now, what's cool about the frequency division, we can start peeling off individual frequencies from any of the subsequent stages. So given that frequency of 10, divided by 10, frequency divided by 10 is our terminal count and our count enable, what's this frequency for this guy right there? Well, if this was 500 hertz, just do the same exact analysis for the second stage as we just did for the first. And if this is 50 hertz, well, Q0, it was half of that frequency, so you're getting 25 hertz. This one right here is half of that, 12.5 hertz. Okay, so generally what you can do is just be like, okay, here is, this is again only for mod 10 there. That's our clock coming in, that's our frequency. This one's always enabled. This is frequency divided by 10. That's f divided by 2, 4, f divided by 8. And because it's a decade, it's f divided by 10. If it was a 16, it'd be f divided by 16. But what's happening here is f divided by 20, f divided by 40, f divided by 80, f divided by 100, and again, same thing here, f divided by 100. And if you want to keep on dividing these things out into all sorts of crazy frequencies, add another stage, make it modulus 6, make it modulus 16, whatever frequency you want, you can get using these cascaded counters. So let's go ahead and just do a quick example of this down below here. And here's a modulus 16 for the low order and a modulus 10 for our high order. What is our total modulus? Again, it's 16 times 10, 160. So we should be able to count from 0 to 159. Okay? So what is, let's say we're going to feed in a 10 megahertz signal right here. What is the frequency of Q0? Well, it should be half of that, so 5 megahertz. What's the frequency of Q1? Well, half of that, so it's 2.5 megahertz. Q2, half of that, 1.25 megahertz. Q3. Okay, so what's Q3 given that it's a modulus 16? Well, it's half of 1.25 megahertz. For modulus 10, it would have been 1/10 of the original frequency, okay? But because we're modulus 16 here, 625 kHz. So what do you do with the TC here? You're feeding it to the count enable. By the way, this one is always enabled. Low order, always enabled. You're feeding it to the count enable of the higher order. What's this frequency right here? Well, it's getting a bit, it's going high every 16 clock pulses. So 10 megahertz divided by 16 still, 625 kilohertz. So now, what's this guy? Well, it's going to be half of 625. Q1, what's its frequency? Half of that. Q2, and now Q3. Yeah, ordinarily with a 4-bit, it's going to be half of 78.13, but we are dealing with a 10-bit counter here. So it's going to, every 10 bits, it's going to get a high on the on Q3 there. And same thing for TC here. It's going to be 1/10 of the original frequency, 625 kilohertz. So you're getting a signal 62.5 kilohertz. I'm missing a K here, sorry. So key thing is just remembering for the different modulus is when does that terminal count go high? It only goes high at the maximum number of bits there once it reaches maximum, or in a particular case of a down counter at its minimum. Okay, so the nuts and bolts implementation of these things. I've just given just general diagrams. Key thing to remember about the nuts and bolts implementation of these, actually physically making them, let's just, again, two 74 190s. How do you actually do this in a 74 190? They're both decade counters. Obviously, if you're doing two of them in Cascade, it's going to count up to 100, or count to 100 positions. Ordinarily, our general system would work, but remember, the 74 190 has an active low count enable and an active high terminal count. So how do we do this? Let's go ahead and draw a 74 190 and another 74 190 in close proximity. So again, we want to go from 0 to 99. So that means we want an up counter. Okay, so what are we going to do to make it an up? We'll ground that. Like I said earlier, that's an active low. That's also an active low. Count enable and an active low load. We don't want to load anything, so tie that to +5. And because we always want our lowest order to be enabled, We're going to tie this to ground. Okay, so now everybody gets the same clock. And now the TC terminal count 474,190 is actually labeled max min. We definitely want to feed that to the second stage, but check this out. It's active low for the count enable. So how do we make this guy an active high? We want to give this guy a low, the second stage here, we want to give this guy a low when this guy has received its maximum. All you do just put an inverter in between them. And again, this guy, we're not going to load anything. And this guy is also grounded there to make that an up counter. Okay? So just keeping an eye out for the actual nuts and bolts implementation of things. 74,190 uses active low count enable, but an active high terminal count. Just keeping in mind on how to actually implement these things using the devices that are available to you. Okay, last thing we want to discuss about cascaded counters is this thing called truncated sequences. So we just figured out how to count to higher numbers using cascaded counters. And let's say using this configuration right here, normally it would count to 0 to 99, i.e. 100 positions. What if we only wanted to count to 40? Okay, so you could do it a couple different ways, by using individual flip-flops, one state. Let's not do that. Let's use the 74,190, 274,190s to actually do this. Well, how you do that is we're going to make use of our data inputs, which we previously didn't do, because remember, our load input here, that was tied to +5. It's an active low load. So we're going to make use of our data inputs and our active low load right now, and a little tricky math to make this happen. So again, we want to go from 0 to, let's say, 39 right now. So that's 40 positions. So ideally, we would like to see our counter go from high order 0, 0, 0, 0, 0, low order to 0, 0, 0, 0, all the way up to 39. And then recycle. So that's 0 to 39. That's our ideal situation. But what if we just started at 60 and counted to 99? It's still 40 positions, right? But you say, wait a second, 99 minus 60 equals 39. Well, remember, +1, because you're including 60, okay? So why don't we just start at 60, 0, 1, 1, 0, quadruple 0, so 6, 0, and count to 99, 9, 9. That's still 40 positions. The trick is how do we start at 60? Use these data inputs right here. Just start dangling 60 off of that. So I'm going to go ahead and redraw this diagram below with a 60 hanging on the data inputs. Okay, so the high order is going to receive a 6. And we're reading MSB to LSB. Low order is going to receive 0. And now what's going to happen is this thing is going to start out. We're going to basically put a 60 on its D inputs, which we just did, give it an active low load condition, and let it run to 99. Now when it gets to 99, we want to reload to start at 60. So once this reaches its maximum, this guy's terminal count, i.e. max min, is going to go high. So what we do is invert that and send those to the load. Bang, you started off loading up with 60 and you're starting back up to 99, okay? In actuality, again, its states are 60, 61, 62, up to 99. But if you really wanted to display 0 to 40, you could do some math, i.e. subtract a 60 and display the results. Okay, so this is how you're basically doing a truncated sequence. If you want n number of positions, in our case 40, just basically take the maximum number, subtract the end, and that's the number that you want to start at for your active low loads. Okay, and you just dangle, in this particular case, 60 off on the data inputs and give it an active low load. It starts at 60, counts to 99, goes back to 60, counts to 99. In our particular case here, when we did full modulus counting, notice that we kept our active low loads at +5 and had no data inputs here. Okay, so that's a quick discussion about cascaded counters, and we're going to move on to counter decoding.